Alright, so again, like in my previous video, I will focus here on paper 1, in which we have a marking scheme, but the idea or concept behind those letters are not given in details. Unlike in other papers where there is enough information already as to how the responses should be done. Alright, this time I will focus on Syllabus 9702, Physics, Component 11 in the May-June 2019 series. If you haven't done this paper yet, pause this video and scroll down to the description. There's a link embedded showing the questions in the paper. Okay, you may answer that one and then play this video again to check your answers. Okay, now for question number 1, this one is asking about the equivalent unit of the base units kilogram square meter per square second. Base units, by the way, are those containing the units of the 7 fundamental quantities, alright, like these ones. From this unit, we can factor the square m, kilogram meter per square second times m. The reason I did that is because this kilogram meter per square second is equivalent to a Newton. Remember that force is product of mass and acceleration. So then we should have Newton meter, which looks like following the equation for work, which is Fd, or force times distance. Work has the SI unit joule that is equivalent to the SI base units kilogram square meter per square second. A is the answer. Now for the next question, we apply the same idea about the SI base units. R here is in this equation squared, so the SI base unit is square meter. This constant sigma, this, has this watt per square meter per Kelvin to the power of 4. The temperature, which is in Kelvin, is raised to the power of 4 in the equation. So we can write K to the 4th here, following this exponent. These, when combined, equals 1. So we just cancel them. These ones too, remove from this very long expression of units. Now, it looks like we ended up with just watt as our unit. Alright, this is an SI unit, but must be converted to SI base units. Remember that watt is a unit of power, and that power is energy or work over time. In question 1, we already know that the unit of work, joule, is kilogram square meter per square second. We just use that and divide it with the unit of time, second. This S, when move up, takes the negative exponent, negative 1, therefore becomes negative 3 for the S's. And this is option C. For the next question, we need to find the magnitude of velocity v here, expressed in the magnitude of v sub v, or vertical component of that velocity v. This one in the diagram, which is also equal to this, and the horizontal component of velocity v sub h. The key to the answer to this question is your knowledge in trigonometry, the Pythagorean theorem from the right triangle here, giving us v squared equal to the sum of the squares of the components, or like that. From here, the magnitude of v therefore is the square root of the sum of the squares. These options, therefore, C and D, showing difference between two squares rather than sum of two squares, can now be discarded. Alright, now for the direction angle theta, we use the definition of tangent. The tangent of an angle is the ratio between this opposite side to the adjacent side. Alright, this is v sub v over v sub h. Alright, here. From trigonometry also, if you want to find the angle, we take the inverse, arctangent of that ratio. So the answer is B. Okay, now for this question, this horizontal line or axis is the time base in the oscilloscope. This time, when there is a complete oscillation, gives the period, and that period is the reciprocal of frequency. The frequency is given, and so we just plug it in, 1 over 5 Hertz. The period therefore is 0.2s, this represented by orange line. Alright, from that, this division, which is half of that period, should be 0.1 second. Since the options are all expressed in milliseconds per division, we need to do conversion here. This 0.1 can be written as 100 over 1000, and 1000 here is 10 to the third power. When move up to the numerator becomes 10 to the negative 3, like that, alright? This power is what we meant by the prefix milli. So we have 100, then this 10 to the negative 3 second, or millisecond per division. The answer is D. When the tire is worn out, as in the case of this question 5, the formula to where the speedometer is calibrated, this one, speed is the distance or the circumference per unit time. But worn out tire would mean that this D is going to be shorter. And based from the data in the question, by 6 over 600 or by 1%. The actual speed therefore is lower by 1% as the circumference is shorter than 1%. Or equivalently, we can also say that the speedometer reading is higher than the actual speed by 1%. This one, A is the answer. Now, in this next question, we first take a look what this one reads, 8 meter per second. Let's draw another line here going to the 1 second time and here at time 4.0 second. We do this because we are to analyze the graph between these times. Okay, we can have a triangle here and a rectangle here with areas equal to half 3 times 14 and 3 times 8. I show the area because of what we need, how far, or the distance covered from time 1 second to 4 seconds. Distance is the sum of these squares. So we have 21 meters plus 24 meters, which is 45 meters. B. This next question is about a cliff and the sea here with, say, this guy throwing the stone horizontally like that. This arrow represents its horizontal velocity and this is the vertical velocity. These are components of the stone's velocity along the horizontal and the vertical. We also note here that air resistance is negligible, so along the vertical it accelerates from 0, increasing value of V, like that. This happens because there is a resultant force along the vertical acting on the stone equal to its weight. And we know that if this is so, then the stone should accelerate, acceleration of free fall. Now along the horizontal, as soon as the stone leaves the hand of the guy, there is no more resultant force, so no acceleration. We say it is moving at constant velocity along the horizontal. Among the options, this graph shows increasing velocity from 0, alright, while VH remains the same. These are what we expected as the stone's motion. The answer is D. Now, question 8 is asking about work. After the charge has been moved 4.0 millimeters, work can be calculated using this formula, provided that D is along the direction of force F. We can therefore write, based on this, that work is F times 4 times 10 to the third power meter. Conversion from the millimeters here. We need the value of force, and we can find that using this equation. Product of charge and the electric field. We plug in values. Charge here is the electric field. Force therefore should be 7.8 times 10 to the negative 3 volt coulomb per meter. Okay, so now we have something to substitute here for force. Let's erase and write that here. This m raised to negative 1 and this m is 1, so we remove. And then 31, which came from the product of 7.8 and 4.0, so we remove these also. And these powers of 10, when combined, give 10 to the negative 6. We copy the remaining unit, Vc, but we know that volt is joule per coulomb, so this is just 1, C over C, leaving us joule as our final unit, the unit of work. After rewriting this figure to the standard form, we have 3.1 times 10 to the negative 5th, option A. Now for this question, we need to recall what Newton said whenever there is an interaction between two objects. There exists a pair of forces of equal magnitude. Apart from that, these third law force pairs must also have the opposite directions. Another important characteristics of the third law force pairs is this, alright? They are acting on different bodies. In option A, the forces are equal in magnitude and opposite in directions but are acting on the car. So this cannot be a third law force pair. Alright? Same with option B, equal and opposite but acting on the same object, the box. In the third option, the force on the plane adds up to 0, making it not accelerate along the vertical, alright, as in options A and B. Now this option B shows equal and opposite forces also. And one is by Earth on Moon, the other is by Moon on the Earth, acting on different bodies. B is the answer. Okay, in this next question, we have to give emphasis in this given information. Air resistance affects the motion of an object. This is a distance time graph, and this curve tells us that there is either constant acceleration or changing acceleration. I say we have here decreasing acceleration because A is equal to F, and this F is the resultant. Imagine that the stone is this, with force on it, this downward arrow representing its weight, and this upward arrow representing the air resistance. We do not neglect this. That resultant force F to determine the acceleration A should be divided by mass M, the mass of the stone, which affects, of course, its weight. Alright? With this idea about acceleration, there should be a change in V, increase in this case. Alright? As in our graph, we have time here and distance here, and the gradient is delta D over delta T. The gradient increases, which is basically the speed of the object. However, that increase happens only till this point, at some value of speed V. Alright? This is because of the resistance R, which increases also as the stone speeds up. There will come a time when the resistance and the weight are already equal, leading to zero resultant force, and of course, zero acceleration. Now, at zero acceleration, there is no more increase in speed, which can be seen from the constant gradient of this line. Now, what happens when we have another stone with their dimension but smaller mass? The weight which is proportional to the mass is weaker this time, alright? And therefore, the value of air resistance equal to the weight can be quickly reached. So the graph here, decreasing acceleration while increasing speed. Then, when weight is equal to resistance, no more change in speed, a terminal speed, and we have a straight line. Alright? Option C. Alright, here is a physics question on collision, and this collision is perfectly elastic, meaning quantities are conserved, kinetic energy and the momentum. From here we can derive, like in one of the previous videos I uploaded in this channel, that the relative speed of approach is equal to the relative speed of separation in a perfectly elastic collision. This means that the difference between initial speeds of the objects before collision, equals the difference between final speeds or speeds after collision. Alright, in our case here, initial speed of atom minus initial speed of the wall equals final speed of the atom minus final speed of the wall. Now, for the wall, both of these are zero, leaving us the idea that the initial speed of the atom and its final speed are equal. And this is given in the problem as V. Alright? Now, how about the direction of motion before and after? Alright? It should be opposite directions. We need directions here because momentum is the product of mass and the velocity, and this velocity is a vector. Alright? Now, the change in momentum, this one being as in this question, is the final momentum minus initial momentum of the atom. Alright? The final momentum, let's erase this, is mass times the velocity minus the initial momentum, which is mass times the negative of that velocity, opposite in directions, alright? Remember? Now, this obviously becomes mv plus another mv, which when simplified gives this option, D. The next question is about an ice floating in seawater. This portion of ice, let's color it red, is submerged in the water, while this portion, blue, is above the surface. Let M1 be the mass of this and M2 be the mass of this portion. The ice is floating, and that if we are to draw a free body diagram, this dot representing the ice is being acted on by the weight W, alright, of the ice, and the buoyant force B, alright. We can say that these forces should yield a zero resultant, meaning buoyant force is equal to weight. Weight W is the total mass, M1 plus M2 times the gravitational field strength G. For the buoyant force, I showed in another video that this can be calculated by taking the product of density of the fluid, the volume of the fluid displaced, and the gravitational field strength. You might want to recall the Archimedes principle, or watch the video again, alright? Now, note that these quantities are related to the water, density of water, and volume of displaced water. The G's at both sides of equal signs can be removed. So we have only the density of water, rho W, times the volume, which is based on the figure, should be equal to pi times the square of radius, times height, which is, in this case, is equal to the height capital H, minus this height lowercase h, equals the sum of the masses, which gives us this whole thing, alright, which is the mass of the ice. We can actually calculate the mass of ice, alright? That is equal to the density of ice times the volume of ice. And this volume of ice from the diagram is pi r squared times the height h, capital H, alright? We have same constant at both sides of equal sign, so we remove those again, leaving us only density of water times H. Distribute that minus density of water times this H equal to density of ice times H. What we need is this H, so we can do transformation of the formula here, and then this. We can simplify this further into H times the quantity rho W divided by rho W, which is 1, minus the ratio between rho of ice and rho or density of water. Alright, like that. And this is option A. Alright, for this question about torque of a couple, the answer is on the definition of the quantity. Torque of a couple is the product of the magnitude of one of the forces multiplied by their separation distance. This one. So we have F times 2D or 2FD as in this option C. Now, for this question, we need to find this distance, and the key to the correct answer is the second condition of equilibrium. The sum of all clockwise moments equals the sum of all counterclockwise moments. So here we have 12.0 kilonewtons times 17.0 meters equals this force, which is the weight equal to this mass 5,000 kilogram times 9.81 newton per kilogram. The weight or the force here is 49.0 kilonewton. Alright, now for the moment, counterclockwise is this force multiplied by the distance. Let's call this distance x. The unit kilonewton then can be removed. Alright, and this figure 49.0 to be placed here at the other side. The x therefore is the result of our calculations here, which is 4.16 meters, the option C. In this question, we need the condition sigma F or summation of forces equal to 0 and summation of moments equals 0 for an equilibrium. The question is which among the four statements must be correct for the forces mentioned in the question, which is necessary or should be true at all times. For option A, forces all act along the same line. When this can be true, three parallel forces can also be arranged differently and have an equilibrium. This cannot be an answer because there are many other possibilities, alright? Now, here in the next option, the three parallel forces have the same magnitude. This cannot be also, since if they do, one possible arrangement could be this, an object, this red here, and the other forces must not be parallel to attain equilibrium, like these ones. This cannot be an answer. Option C is related to the one that I mentioned in option A. When these other combinations are possible, the statement excludes the possibility of having equilibrium while forces are along the same line. So this is again not a must, not true at all cases. The correct answer is D here, alright? They do not all have the same magnitude. In a sense, this is a combination of option A and option C, alright? For this question 16, we need to see that we have equal volumes to be considered in our solutions. This beaker is used to measure the mass of both the water and the cooking oil, and both fill the entire space of the beaker. That volume, let's call it V, alright? For the density of water, 1.00 grams per cubic centimeter equals the mass of the beaker in the water minus the mass of the beaker all over the volume V equal to the density 1.00, and this tells us that V is actually 258 cubic centimeter. Now for this question about the density of the cooking oil, we know that the density is mass over volume. We just need to plug in values for mass, which is 351 minus 103 grams divided by 258 cubic centimeter volume. The density of cooking oil, therefore, is 0.961 grams per cubic centimeter. Option A. Alright? Now in this question, we need to find the work. And we know that work is equal to the product of force and the distance parallel to the direction of force. If this is the distance D along the horizontal, then the force needed is the component along the horizontal too, alright? Therefore, we should use this, alright? Force cosine theta, the component along horizontal, times the D. Or rearranging it like this, FD cosine theta. A 100 Newton multiplied by 5.0 meter cosine 30 degrees is 430 joules. This is the answer. Now, question 18. For the derivation in this question, you may want to consider watching the video I made. Alright, it is in this channel. If you have already watched that, you should have seen that I started the derivation from this equation in option C. Both sides are to be multiplied by 1/2 of the mass, which gives us an equation 1/2 mv squared equal to 1/2 mu squared plus mass acceleration times the displacement. Note that in the case of this question, all values to be used are magnitudes of velocities, acceleration, and displacement. So the v and u can also be called speeds, final and initial. And s here is the distance instead of displacement. Alright? Now see this option A? F is equal to ma. There is ma here. We will substitute F for that ma. And so the equation is now half mass v squared. V is the final speed equals half mass times square of its initial speed. Okay, maybe we can just move this to the other side. So minus half mu squared equals Fs. The ma has already been replaced by F. Alright? This option D can then be used next. We have Fs, and that is equal to the work W here. Now you see that option A is used, option C, and option D. So by elimination, our answer should be B. But let me continue with this one, okay, by recalling the W equals to change in energy, delta E. Delta E is the final E minus an initial energy. By inspection of the terms here, if these are energies, then these are also energies. And these energies are related to the motion or speed. Our term for that is kinetic energy. Final kinetic energy minus initial kinetic energy here. That is how the equation was derived, alright? Alright. Now, normally in questions about power and mechanics, students would immediately use this equation, power equals force times speed. Let's see if we can make sense of this one in relation to this question. We know the value of V, but we do not know F. So we will use the definition of F, or the force, using the information given here, including mass and time, alright? This delta P, or change in momentum, is the grasshopper's mass times the change in velocity. So we substitute those so that we have 0.12 grams times the change in V, which is 3.0 meters per second minus 0, all divided by the time, which is 0.020 second. Now, since the option have SI unit, we better convert all our data into SI units also. So this in grams to kilograms is going to be 0.00012 kilogram. Our force therefore is 0.018 with Newton as its unit. Now imagine that this was the grasshopper on the ground, and that when it jumped, it used the leg till this height, where we have those velocity and time values in the question. We can say that we have an instantaneous power here due to force 0.018 Newton. But that is not the same power between these two lines, alright? It should vary since the force is not constant in the interval. Reason why I try to draw this spring. It is similar to that. Force here varies from 0 to that computed value, alright? We can also say that power varies directly, just like the force, alright? So how do we find the average? Alright, as a side trip, imagine you have values of constant interval from 0, 1, 2, 3 to 4, alright? Usually, the average is determined by adding all these divided by the number of cases, or 5. Or, an alternative to that, assuming that the values are increasing at the same rate, we can just take the range, highest which is 4 minus the lowest which is 0. Then, divide by 2. Now, you'll see that the answer is the same. Now, it looks like we can use this alternative way, alright, to calculate the average to answer the question. Find the power here at the highest F, which is 0.054 watt, minus 0 in here, on the ground, divided by 2. Alright, so the average power is 0.054 watt divided by 2, or 0.027 watt, which is option C. Now in the next question, we deal with the spring, alright? And this triangle here is the one that would help us answer the question, alright? In a force versus distance time graph, the area under the graph is the work done on something, and will become the change in the energy. When we compress the spring, energy is stored, potential form, amounting to the work you did to compress it. So here, the stored energy, represented by delta E, is the area half 6 Newton times 30 millimeters. But we need to express our answers to the SI unit joules. So we have to make all the quantities to be substituted be expressed in the SI units. This 30 millimeters should then be converted to meter. 0.030. Simplifying the equation, we should have stored energy equal to 0.090 joules. Alright, this option. Now in this question, apart from the elasticity, the Newton's third law of motion comes in play. Alright, if there is a force here, with that law, we should see that this other material, steel, is also experiencing the same amount of force, 40 Newton. The total change in length, or the extension, is the sum of the extension of the steel and the extension of the brass. We are given the Young modulus of the two materials here also, and that from Hooke's law, we know that this constant equals the stress or force over area divided by extension over the original length L. Alright, we can write this equation as E equals F over A. Instead of dividing, we multiply the reciprocal, L over extension delta X, which when manipulated further gives us an expression for the delta X. Alright, this one. Now we will use that expression for the total extension, FL over delta E here. But for the steel, we have to put subscripts, alright, S, plus the same thing here, alright, force F on brass times original length of the brass divided by the product of the area A and the Young's modulus both of the brass. Alright? Now, note that the cross-sectional area is the same for both materials. So we just call these A, removing all the subscripts as anyway we have the same value. Alright? Now for the constant E, this in brass and this is in steel, we can see the relationship. If we say the E of brass is E, then the E of steel is twice that E. Let's write just E here. Alright? Here. 2E. The force experienced are equal, 40 Newton here and also 40 Newton here. So same way, just F, no need for subscript. Those common between the two terms, we write here, times half the original length of the steel plus the length of the brass. After plugging in values for the common variables in each terms, alright, you should get 1.7 times 10 to the negative 4 times the sum of half of 0.80 meters and 1.4 meters, which is 1.8 meters. This gives the final answer 3.0 times 10 to the negative 4 meters. Alright? The answer is B. For this next question, we need to recall the difference between a displacement versus distance graph and displacement versus time graph. One thing that you can think about this graph is that it is a snapshot. Meaning, the moment you saw the wave, you take a photo of it and you have this picture, the graph. You have their positions all at the same time. Particle is here, this, and then another here, another, and the others also. All particles at that very moment of the snapshot. Now, since the horizontal axis is distance, then this length, which a particle could have traveled till it has the same displacement again, is the wavelength. We have here 4.0 centimeter. Now, for the displacement versus time graph, we plotted the positions of a single particle at different times. Say at time equal to 0, the particle was here in this graph. The same in this other graph. After some time, here, alright, equivalently, here in the other graph. Because now, we plot displacement against time. Again, after a certain time interval, here, or here in this other graph, and also here, and here. We should see that the amplitude A can be determined from any graph. Alright? And they are equal. Now, for the other graph, the time or the period, which is usually of greater interest to people when it comes to this kind of graph, this T is represented by this length along the time axis. Period is the time for one complete cycle. So all this yellow portion in the time axis can be called period. The answer to the question is the one with period T equals wavelength, this, divided by the speed, this value. The period is 0.20 second. So the answer is A. For the next question, we have another displacement versus time graph, a snapshot. If we are to make another snapshot at another time, we will have this, that blue graph. From here, we can also claim this idea that the change in time, delta t, is the same for all particles A, B, C, and D from the time difference between the two snapshots. Now, how can we find the fastest particle moving upwards from this information? Alright, from these snapshots, A looks like went from here to here. Alright, particle B from here to here, C went there, and for D, initially it was here, but seen here in the next snapshot. Alright, D and C went downwards, obviously. So either of these cannot be an answer. Now, since they are all having the same delta T, and within that same delta T, this particle A covered greater distance, this one, we say that it is faster than the remaining other option B. Alright, the answer is A. Now, this question, we have a tube here. Let's copy that here. Now, imagine that when the water falls to here, the sound produced by the fork makes a stationary wave like this, where this point is the node N and the antinode is here. Alright? Remember that in stationary waves, the amplitude varies. 0 at nodes and maximum at antinodes. Remember that the amplitude is related to the loudness. High amplitude gives loud sound. So we therefore hear loud sound in this case when the water level is, say, like this. Alright? Now, when the water level is here, where we can create another stationary wave like this, we can again have another loud sound. See, they resemble each other here, antinodes at the opening of the tube. Now, this line and this line is the change in water level between loud sounds and is 32 centimeter. We can see from the diagram here that this 32 centimeter is actually half the wavelength. Therefore, the wavelength is 64 centimeter. Now, for this question, we should see or assume that the water has constant depth. And so we have water wave speed that is constant. Otherwise, or in other questions, you may need to consider refraction when it goes from deep to shallow water or from shallow water to deep water. This frequency is observed frequency. We can say that the observer is at this position X. When the insect is stationary, the wavelength distance between two fronts is same throughout. But as it moves towards the observer at X, fronts are closer to each other, and therefore the wavelength is smaller or shorter. Now, wave speed is given by the equation wavelength times frequency, and that since the speed is the same, a decrease in wavelength would mean an increase in frequency. The answer is D. This change in frequency perceived by an observer due to relative motion between the observer and the source of the wave is called Doppler effect. Alright, and in this next question, question 26, is again about this phenomenon. Alright, the formula for this is observed frequency F sub O equals the sum of the speed of the wave V and speed of observer V sub 0 all over the sum of speed wave V and speed of source of wave V sub S multiplied to the frequency of the wave F. We should also note that these involve relative speed, so the direction of their motion also matter. So in this equation, this is written to have plus and minus here also. Now, our observer is standing at rest, alright? So we can just remove this V sub O here. That's 0. When using this formula is that positive is used when source is going away from the observer. And the minus when the source is moving towards the direction of the observer. Now, these two options are possible answers to the questions. Here's the clue. We can verify that from the equation also. The F is 2.0 Hz and then observed as 3.0 Hz, it becomes higher. These two in the equation tells that a higher F sub O or observed frequency means that the relative speed should be small, inversely proportional. That happens only if we operate by subtraction, minus here, alright? The source is approaching directly towards the observer. Now, let's use the equation to calculate the speed. Plug in 3.0 Hz for F sub O equals 1.5, the speed of the wave, divided by speed of wave again, alright, minus the speed of the source times the frequency of wave, which is 2.0 Hz. 3.0 divided by 2.0 is 1.5 equals 1.5 over 1.5 minus speed of source, which is given the symbol V. Simplifying it further, we have 1.5 minus V equals 1.0 or V equals 0.50 meters per second. B is the answer. For this question, we use blue for a diagram of one progressive wave and a green wave of same frequency, superimposing to produce a stationary wave like that. This is a node. Here is another one. From the diagram, it looks like the separation distance between the adjacent nodes is half the wavelength. So lambda, or the wavelength, is 3.0. Now, to calculate the speed of the progressive waves, we use the formula V equals lambda F, where F is 300 Hz. 3.0 m times 300 Hz is 900 meter Hertz or 900 meter per second, D. Now let's move here. When you do an experiment in a ripple tank, the water level is usually assumed to be the same, alright? And therefore, speed is constant. The frequency of the wave is also constant, which means that the distance between the two adjacent fronts, whether it is before diffraction or after bending through a gap, is also constant. The options are showing us those distances, the wavelength. This option is not the correct answer because the distance here, the wavelength, is different from here. Shorter. Here, longer. So, not a possible answer either. Same here. Our answer therefore is B. The diagram shows that the fronts are all equally spaced, alright? Meaning the same wavelengths, alright? Now, number 29. Here, I need to draw some fringes, alright? Here, over this screen. This distance is 4 millimeters as mentioned in the question. And this is usually represented by variable x. Fringes separation. We have another distance here. This is given the variable a, representing the slit separation. Another distance from the slits to the screen is this. We use capital letter D for that, alright? In the lab, activities determining the wavelength of a source through double slit experiment, all these distances can be measured, and that wavelength lambda can be calculated by multiplying a and x over d. Now, we have two experiments in this question. One, we represent using data plugged into the formula. So, lambda is 4a divided by d. Next is lambda equals x, the fringes separation, that is as here, times the half of a divided by 2d because of this information. Now, let's combine these two. Wavelengths are the same. So, 4ad here equals this expression from here. We can just remove the d here, alright? Cancels each other's effects in the calculations. Same with the a, leaving us only 4 equals 1/4 x. X is therefore 16 millimeters, d. For this question, let us recall the related formulas first. For the double slit experiment, d sine theta equals n lambda. For the diffraction grating, lambda equals ax over d. Now, based on the situation in this question, we can combine these two formulae. D sine theta equals n times lambda. This expression from the other equation. But we know that d is 1.0 m and a is 500 d from here. And the angle is 30 degrees when n is 1 from here. Alright, 30 degrees and first order relative to the normal. So the d times sine 30, which is 0.50, equals 1 times 500d times the x or the fringe separation divided by d, which is 1.0 m. Cancel the d's. X therefore is equal to 0.50 divided by 500, which is 0.001 m. When rewritten to follow the scientific notation or standard form, some do that by moving the decimal place and use the corresponding exponents like here, gives this option, C. In this question, we use the convention for field lines around the negative charge. You should know that by convention, a negative charge like electron, the field lines are inward, like these, alright? The answer is A. Question 32, the key to the answer to this question is the idea that charge is quantized. It must be a factor of E, this magnitude, which is the charge of a proton given a positive or an electron, negative. A particle is likely not going to have a fraction of that magnitude as its charge, alright? Option A here looks like a result where a particle gained 3 electrons. Option B lost 1 electron. Option C lost 2. Its charge is now negative 3.2 times 10 to the negative 19 coulomb. Option D is the answer. It is not quantized. Alright, circle this. Now here we know that a volt is a joule per coulomb, and that by looking at the options here, all are referring to 1 joule of work. Here, 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 and here. This means that the particle considered moving between 2 points P and Q has a charge of positive 1C. So either of these two are not going to be an answer to the question. In reality, guys, charges moving along the electrical wires are actually electrons. But remember that all results of analysis and computations will be the same even if you consider conventional current instead of electron flow current. Conventional current assumes that positive particles or charges are the ones moving. Alright? Imagine these two portions. We have positive charges. Now, which way? Should we consider the charge move from P to Q or from Q to P? Now, to figure that out, let's use an analogy here. Imagine the ground here, and we have a mass, this red dot. This is a force acting on that mass. To move it a distance d. Can we use this information to determine the work? Perhaps we can, but we know that gravity is also there in addition to this force F. In fact, the gravity alone can move the mass down to the ground and does the work. No need for force F. Now, if the mass is on the ground, alright, it cannot move up on its own. We have to exert a force of at least equal to its weight, alright, in order to move that upward. In this case, we do have a work due to force F, alright. Similarly, this applies to these two charges, and this one at the left appears to be like this first case I explained. This is not about the volt by definition, the joule of work to move a coulomb of charge between 2 points. It should be this one at the right, from low potential, like the low potential here in our analogy, to a higher potential, or equivalently to point P. The answer is B. Now, 33 is a question about the characteristics of filament, an example of non-ohmic material. Ohmic materials have this kind of graph, a straight line when V and I are plotted. For filament lamps, line or graphs also passes through the origin, meaning when there is no V, then no current I. But you may see a small portion in its VI graph that looks straight. Alright, a small portion where resistance is constant. In most parts though, since filament becomes hot at high voltage and current, resistance increases. Hot objects have particles moving very fast, which could provide additional resistance to the flow of electricity. Now, remember that resistance R is the ratio between voltage V and current I. Should we expect a curve? Yes, because there is an increase in resistance. Let's do a quick check first. This one, line passes to the origin. All options satisfy that. Now this, it looks like these two don't have these characteristics. So eliminate these options. For this option A, we have here a straight line graph. Same with option B here. But do the rest of the graph shows increasing R? Alright, let's see here. Consider this line here. And this one too. Also this. And here as well. The gradient here decreases. In this other remaining option, option B, these lines between close points look like this. And this, and these. Gradient of these lines are increasing. The gradient in a V versus I graph represents a resistance. Filament has an increasing resistance when temperature increases at higher voltage V and current I. So our answer here is B. For this question, let's draw a circuit diagram using information given. Here is the battery with internal resistance R and some other components here, say two resistors with PD. The voltage across these 2 points is the terminal PD and is equal to the EMF minus the potential difference across the internal resistance. It says here that the internal resistance or R increases, so it takes more energy per charge. This means that the terminal PD from the equation here decreases. More volts are taken by the higher internal resistance. So these are possible answers, A and B. Now the power output is related to the terminal PD, and since the terminal PD has decreased due to that more power lost to the internal resistance, then the power output also decreases. So A. We should draw two circuits in this question 36. One is this, cell with internal resistance R is connected to a resistor. With this setup, the current is 1.00 ampere. When an identical resistor is connected parallel like this, the current becomes 1.93. This current should be the one here, alright? Otherwise, you assume that it is the one passing through each of the branch. The internal resistance to satisfy that assumption would be such that its PD exceeds the EMF. That doesn't make sense. So current should be here, not along any of these branches. For the first diagram, we can see that the EMF equals the voltage across resistor R plus the voltage across the internal resistance R. This simplifies to epsilon or EMF equals 3 plus R. After substituting 1.00 ampere for the current and 3.00 ohm for the resistance. We can check these options using this equation and see if we can eliminate options. We add 3 here, alright, here, and here. Looks like all satisfy the equation. The EMF equals 3 plus the internal resistance. Note guys that I am only looking at the figures. Do not be confused with the units, as these is supposed to be 1.00 A here multiplied by R, and this 3 has unit volt. Alright, so we cannot do elimination here. Let's proceed and use the second diagram. The reciprocal of the combined resistance is 1 over R plus 1 over R, where R is 3.00 ohms. Combined resistance therefore is 1.50 ohms. Now we can follow the formula from the first diagram as they are resembling each other now, with R 3 ohms here but 1.5 ohms here. In current values, 1.0 ampere here and 1.93 here. EMF equals 1.93 times 1.50 plus 1.93 times the internal resistance R, following that formula. Now, we do some stuff related to simultaneous equations you learned in your mathematics. Elimination method. These equations here. This one minus this one. 0 for epsilon minus epsilon equals, this is from 3 minus this product of I and R, 1.93 times 1.50. Then, this R minus 1.93 R or negative 0.93 R. Internal resistance R therefore is 0.105 divided by 0.93 or 0.930, which is 0.113 ohms here in this option. The EMF is that added to 3, which is this. Alright, C is the answer. Now 37. For this next question, let me say that there are circuits that are usually used in devices and that shortcuts to determine several quantities have been derived. One example is the potential divider, when we want to determine the voltage across a specific component in series with the others. Alright, in this question, we will consider the current divider, but this applies in a circuits with components that are parallel to each other. And we want to find the current passing through a particular branch. Here we want to find the current passing through X. This is I sub X. This I sub X can be determined by dividing the total resistance by the resistance of the component we want to find the current. This R sub X here, times the total current. These resistors are identical. Same resistance, so the resistance of this branch is 2X. Now we find the total resistance. 1 over RT is equal to 1 over X plus 1 over 2X. LCD is 2X and here 3. So our resistance is 2/3 X. Divide that by the resistance here, X, times the total current, which is 0.38. Therefore, in the end, the current passing through this branch with one resistor only is 0.020 ampere. This is our answer. Now, this potential divider, the formula will be used in the next question here. This is the output voltage, input voltage. This is the resistance of the component from which we want to find the voltage across. Alright, R. The formula is V sub O equals that resistance R over the total resistance in series times the input voltage. Now, for the range of possible output voltages, those can be determined by considering R equal to 0 up to the R equal to 20, minimum resistance and the maximum resistance. From the formula, we can easily see that output voltage is 0 when resistance is 0. Alright? And when the resistance is 20 ohms, output voltage is 20 over 40, sum of the two 20 ohm resistors, alright, times 12 volts. This is 6.0 volts. Range is from 0 to 6.0 volts. The answer is A. For this second to the last question, recall that the nucleus is very small, positive region at the center of an atom. Neutrons and protons can only be found there. The rest are electrons and mostly empty space in an atom. These hadrons are held together by strong nuclear force in that location called nucleus. The other options are possible observations in an alpha scattering experiment. Alright? This option A, however, is the only one that supports our understanding of nucleus, following the fact that alpha particles are also positively charged. Alright? Now, for this last question, note that this magnitude, positive 1.6 times 10 raised to the negative 19th power coulomb, is usually denoted by letter E. You may look at this as the charge of a proton. The negative of that is the charge of an electron. The given quarks in the options in this question are the up quark, which is believed to have a positive 2/3 E charge, down quark, which is negative 1/3 E charge, and strange quark, the same magnitude, negative 1/3 E. Option A, up, down, down, is the quark model for a neutron. Alright, we can verify this by looking at the charges of the quarks. Here we have positive 2/3 plus 2 negative 1/3, which sums up to 0. A neutron has no charge. This is not the answer. Next option is positive 2/3 E also, plus 2 negative 1/3, which is also 0, so eliminate this option again. The third quark is quark model for a proton, having 1 E charge or positive 1.6 times 10 to the negative 19 coulomb. Let's verify that by writing here 2 ops or 2 positive 2/3 E plus negative 1/3 E, 1 E charge, or this value. This is not the answer also. It is now obvious that option D is the answer. If you are to follow the same technique here, adding those equivalent charges of each quark up will give you 2E. D is the answer. Alright, so those are the 40 questions in this paper 1 in this June 2019 series. I hope that you learned something. Bye.